Okay, metamorphism happens. The rocks change texture, they change mineralogy, and we report or collect data on those changes. And we like to report what's the intensity or what grade or what level of metamorphism that rock got to. One of the ways we look at it here with grade is from low grade to high grade. Across the top is contact metamorphism. That all happens at high temperatures, but it can be a low grade temperature, an intermediate grade, or a high grade temperature. Mountain belt metamorphism happens at a low temperature and pressure, a intermediate temperature and pressure, and a high grade metamorphic rock. And mountain belt metamorphism could happen at a high temperature and high pressure. The highest pressure ones are the subduction zone metamorphism rocks, like the blue schist facies. Those are going to occur at low temperatures and really high pressures. We can plot on this graph where our rock would fit. In the field, when we're mapping rocks, so this is a geologic map, but special in terms of metamorphic minerals. So it's a geologic map of metamorphic minerals, not geologic formations. And what we're looking at as a geologist walked around in the field with a hand lens and identified all the minerals that were indicative of pressures and temperatures. We call those the index minerals. They're either geothermometers or geobarometers. They tell us temperatures and pressures. So cordierite would be the highest grade, and then biotite chlorite the lowest grade. If you can imagine connecting the dots here, the cordierites and the silmonite, orthoclase, silmonite, muscovite form the core of the Appalachian Mountains in the middle, and then coming off of it are lower grade rocks. So it's pretty symmetrical across the core of the Appalachian Mountains. The boundaries between the different minerals are called isograds. Another way to look at intensity is the facies. The facies are these temperature and pressure zones on the graph where certain mineral assemblages form. You know the protolith, and that protolith has a certain chemistry to it, and when it metamorphoses at different pressures and temperatures, different minerals are going to grow and be stable at those pressures and temperatures. So we're able to plot and say a certain rock is it green schist facies, amphibolite facies, granulite facies, and here they have plotted 1, 2, 3, 4, 5 to coincide with different parts of a plate tectonic setting where plates are coming together, convergent plate boundary. The name of the facies, green schist, amphibolite, granulite, blue schist, those are all based on the dominant mineral that you would find at that pressure and temperature.